In a world dominated by large language models, it's not just the size of the model that matters, but also the quality of the data it's trained on. We are talking about data sets that can reach sizes of 100 millions, if not billions of tokens. But here's the burning question. Are all these tokens really equally important? Hey Internet, welcome back to the channel. Today, we are diving into the fascinating world of language models and exploring a groundbreaking new approach called selective language modeling. But before we delve into its specific, let's understand the challenges of traditional language model training. Imagine you're tasked with training a language model. You gather a massive data set, news articles, social media posts, code repositories, everything. A true feast of text data. You feed it all to the model, hoping it will learn the intricacies of language. This approach, while effective, has limitations. It's akin to a student cramming for an exam. The model ingests everything without discrimination, potentially wasting time on irrelevant information like punctuation variations or overly common phrases. This not only hinders training efficiency, but can also lead to suboptimal performance on specific tasks. Selective language modeling tackles this inefficiency head on. It acts as a personal trainer for your language model, ensuring it focuses on the most valuable information within the data. It follows a three-step approach. The first step involves training a separate model, often referred to as the reference model. The model serves as a benchmark and guide for the main model. We train the reference model on high-quality data that reflects the desired outcome for the main model. To put it in an example, imagine you want the main model to excel at solving mathematical problems. The reference model, in this case, would be trained on a dataset of solved mathematical problems with explanation and reasoning steps. This reference model establishes a baseline for what the main model should be learning. The next step involves token level analysis, where things kind of get more granular. We break down the training data for the main model into individual words or tokens. Think of these tokens as the building blocks of language. Using the reference model, we analyze each token's importance. We compare how the reference model predicts each token and with how the main model predicts it. This comparison provides a score for each token, indicating its level of difficulty for the main model to learn. Try to imagine this analogy. The reference model, like a seasoned linguist, examines each word and assesses its complexity. It might say, this mathematical term is crucial for solving problems. The main model needs to understand it thoroughly. Conversely, for other tokens, like common prepositions, the reference model might say, this is a very basic word. The main model likely already has a good grasp of it. Finally, the core principle of SLM comes into play. The main model focuses its training on the tokens with the biggest difference between the reference model's prediction and its own. These are the knowledge gaps that the model needs to bridge. It's like the main model, acting as a student, dedicates more effort to mastering the complex mathematical terms identified by the reference model, the seasoned linguist. By prioritizing these high-impact tokens, the model optimizes its training by focusing on the most valuable information for the desired outcome. This research introduces a new language model called Rho1. This model is specifically designed to benefit from the advantages of selective language modeling. Rho1 is trained using SLM approach we just discussed. It leverages a reference model trained on high-quality corpora to identify tokens that are most beneficial for downstream applications, particularly tasks like solving mathematical problems. By focusing on these crucial tokens, Rho1 demonstrates significant improvement in efficiency and performance. One of the key innovations in language modeling research focuses on how tokens, the building blocks of language, are learned. Previous research often assumed that tokens with little change in perplexity were already learned by the model. However, this study sheds light on a more nuanced reality. They categorize tokens into two different types, easy tokens and hard tokens. Easy tokens are readily learned by the model during training. They might be common words or basic grammatical structures that the model grasps quickly. Hard tokens, on the other hand, pose a challenge for the model. They might be complex vocabulary terms or concepts that require more training iterations for the model to understand effectively. These hard tokens can be categorized based on their loss trajectory. Persistent high loss tokens consistently exhibit high loss, indicating the model struggles to learn them. And then there is increasing loss tokens, which surprisingly show an increase in loss during training. This might be due to factors like high aleatoric uncertainty. The benefits of SLM are multifaceted. Remember the student cramming for an exam? With SLM, it's like the student focusing on key concepts instead of irrelevant details. The model spends less time on redundant information and more time on mastering crucial aspects, leading to faster training times. By prioritizing valuable knowledge, the model performs significantly better on specific tasks. Take the example of training for math problems. With SLM, the model focuses on the mathematical concepts and reasoning patterns, leading to improved accuracy when solving problems. This targeted approach translates to better performance across various downstream tasks. The effectiveness of SLM has been demonstrated through extensive testing on various mathematical reasoning benchmarks. Study shows that SLM significantly enhances token efficiency during pre-training. This means that the model learns more effectively with less data, focusing on the most relevant information for mathematical reasoning. SLM leads to significant improvement in performance on few-shot mathematical reasoning tasks as well. For example, research shows that SLM can improve average few-shot accuracy on datasets like GSM8K and math by over 16%. This translates to achieving baseline performance 5 to 10 times faster compared to traditional training methods. These results highlight the potential of SLM in revolutionizing few-shot reasoning capabilities in language models. By focusing on critical tokens and optimizing training for specific tasks, SLM opens doors for more efficient and powerful language models, particularly in domains requiring strong reasoning skills like mathematics. Researchers are actively exploring ways to further refine and extend the capabilities of SLM, and some of the exciting possibilities are reweighting tokens. So what it means is that instead of binary classification of important or not important for tokens, researchers are exploring assigning different weights based on their level of importance. This allows for a more non-training approach, similar to a student assigning greater focus to particularly complex concepts. And then there is reinforcement learning as well, which basically means the use of a reference model as a reward model is being investigated. This could guide the pre-training process using reinforcement learning principle. Imagine the reference model acting as a wise teacher, offering positive reinforcement when the main model grasps crucial concepts. Researchers are also considering adopting multi-reference models to address potential overfitting issues. Additionally, designing token-level curriculum learning strategies could be beneficial, creating a structured learning path for the model. Implementing iterative strategies for continuous improvement in SLM is another promising direction. This would allow the model to constantly refine its learning process, akin to a student continuously seeking feedback and improving their study techniques. These potential extensions of SLM hold immense promise for the future of language models. By optimizing training efficiency, enhancing performance, and addressing challenges like overfitting, SLM paves the way for even more powerful and versatile language models that can excel in various tasks and applications. The concept of SLM builds upon a rich foundation of research in language modeling. And some of the areas of related work are scaling laws, where researchers explored how factors like number of parameters, data size, and computational power impact language model performance. Understanding these scaling laws is crucial for optimizing the model training. Language model training and dynamics have been also investigated the internal workings of language models during training. This includes examining how the model acquires linguistic knowledge and how its behavior evolves during the training process. Data selection and optimization. Extensive research focuses on improving the quality and efficiency of data selection for pre-training language models. This involves basically ensuring data quality, diversity, and alignment with the desired learning objectives. Techniques like data filtering, deduplication, and curriculum learning play a vital role in this area. These areas of related work provide valuable context and contribute to the ongoing advancements in language model training. SLM leverages these existing research areas and introduces a novel approach to focus on high impact tokens, leading to more efficient and effective learning, particularly for few short reasoning tasks. If you found this exploration of SLM interesting, be sure to give this video a thumbs up and let us know in the comments what other areas of AI you would like to see us delve in next. Don't forget to share this video with anyone who might be interested in the future of language models. And if you're new to the channel, consider subscribing for more exciting dives into the world of artificial intelligence.